Okay, guys. So as promised yesterday, I'm going to do a video on volatility, which I'm doing now, and I'm going to share in the group. I just hope this thing is recording. Let me be sure. Record and transcribe. Stop recording. Okay, I guess it's recording. Stop sharing. Okay, I shared my screen as well. Okay, so today, very briefly, I'm going to talk on volatility. Most importantly, we'll talk about the properties of financial data, and then we'll see how to model volatility. We'll see the Garch model, the Egarch model, and the Fiegarch model, just three of them. And then at the end, we'll see how we can compare these models to know which of them is the best after estimating each of them separately. Then we will also see how we can obtain the volatility variable, that is the conditional variance, which we can use for other things, and also the graph. I'll show you all of this. So first things first, before I get into it, I'm going to use the first 5 or 10 minutes to give you an overview of everything, as I always do. So as I mentioned to you some time ago, normally types of data, as you know, we have time series data, we have cross-sectional data, and we have panel data, right? So I'm not going to talk about cross-sectional and panel. I'll focus on time series data. Now, with time series data, of course, you know, this is data for one subject over a time span, a period of time. Okay, we also have financial data. Financial data. Actually, it's not like financial data is different from time series data. Financial data is really time series data, but we will put it separately. We will look at financial data separately. Why? Because it has some features. Now, most of the time series methods, econometric methods, they assume linearity. I'm just giving you an overview. I'll get into the main things very, very soon. Most of the time series methods, they assume linearity. These are linear models. But with financial data, because it is high frequency data, financial data is high frequency data. By high frequency, what do I mean? I mean, we have observations more than one time in a year, many times. For instance, if you have annual data, you have one observation every year, especially these macroeconomic variables, yearly data. But with high frequency data, we can have monthly data, that is every month. We can have quarterly data, daily data, even minute by minute data. So because of this high frequency data, there are a lot of problems. It has some features. Some of the features of high frequency data are, for instance, as we will see when we will look at the properties, we will discover that it is typically not normally distributed. It is typically leptoketic, which means it has positive excess ketosis. I will explain better. And also, most importantly, we have what is known as volatility clustering. Volatility clustering. These are some of the properties of high frequency financial data. Because of these properties, we cannot use traditional time series econometric methods to model this kind of data. So we need to model it differently. For instance, you know, with traditional time series methods, like the classical linear regression model, first of all, linear, you see here L, we expect that there should be linearity. But with financial data, typically it's non-linear. There is no linearity. And also, with the classical linear regression model assumption, we expect that there should be no heteroskedasticity. That is the variance of the error terms should be constant. But with financial data, we have volatility clustering. This volatility clustering is actually heteroscedasticity. They call it autoregressive conditional heteroscedasticity. That is ASH. Autoregressive conditional heteroscedasticity. This is common with financial data. So because we have this heteroscedasticity, conditional heteroscedasticity, we cannot use, for instance, ordinary least squares because we will be violating this classical linear regression model assumptions we should know. So we need to model the data differently. Okay. If you have that idea, then I think I should go straight now to the data so we can start seeing what is happening. So I downloaded market index data from Yahoo Finance. I just downloaded data now for the NASDAQ 100 index. This is a market index in the US. Let me show you. I have it here. So you see the NASDAQ 100 is a stock market index, which is made up of 101 equity securities issued by 100 of the largest non-financial companies which are listed on this stock exchange. So this is a market index which I just downloaded from Yahoo Finance. So I have the data here on Excel. So you see it is daily data which I have downloaded from 1985 right down to, let me see, I think I downloaded like 3,000 something observations. From 1985 right down to, I think 1998 or something, yeah. So totally 3,000 something observations. So we have the prices here, the market indices. This is the adjusted closing price. Adjusted close price. So this is the prices for the market indices. Now, we are not going to use these prices in our analysis. We need to calculate returns. We need to generate returns from these prices. And how can we generate the returns? On Excel, what we do is, like, I'll put the formula equals to 100 times open brackets current price divided by previous price. For instance, this is the current price divided by previous price. So I will click one space above. I press enter. Of course, you discover that here there's no value. There's no value because remember the previous price is one space above where there is no value. So what I can do is I can just put my cursor here and just double click, and I will have the returns for all observations. So for this, if you check here, you see the formula 100 times current price divided by previous price. If you check this one, for instance, you see 100 times the blue current price divided by the red previous price. So this is the return series. The first observation, we lose it. So when you take returns, you will lose one observation. So we are going to lose this first observation. So if I like, I can delete it, and maybe I can write here returns. You can name it anyhow. I'll just put there return, which means return series. So this is our return series. Now we are going to use this return series. Okay. To do this analysis, we are going to use Osmetrics software. So please, I don't know, you guys should try and get the Osmetrics software on your laptops. I have it here already. This is the software, Osmetrics. We can also do this volatility. We can also model volatility using eViews, but Osmetrics is a better software than eViews as far as I know. We are going to use eViews just for one thing. When we will try to model the volatility using the Garch-Type models, we are going to use eViews to get the AROMA. Let me write it. arrow MA order. That is the AMA order. We'll get it from eViews. I'll show you. Okay. So now back to Excel. I have my return series. So I'm going to open Osmetrics. I'll open the software. Okay, so this is the software. I'll come to File, come to New here. I'll take the first option here, Data, because I want to import my data to Osmetrics, and I'll click OK. Here, typically, you can change it, but I'll leave it as annual undated. Then even with the start date, by default, Osmetrics will always put 1996. So leave it as 1996. No need to change it. What is important is that you should indicate the number of observations here. So I'll check Excel file. Observation 2. I'll type count. I'll use count A function. You see this count A? Count A. Then I will check the column where I have my data. You see, my return is found in column C, right? So I'll put here C, column C. If I do that, you see it highlights the column. If it was in column D, instead of this CC, I'll put DD. So once I do that and I press enter, it tells me the number of observations. Here we have data, but it is not an observation, it is not numerical data, it is like return. So this cell is included in this 3,163. So if I subtract this one, it means I have 3,162 observations. That's how I do to check the number of observations, but you can manually check how many observations you have. Okay, so we have 3,162 observations. So I would directly write here 3,162 observations. And I click OK. Next, I have to copy the data. I can delete this. Copy now the data, the return series. It's the return series we are using. I have to copy the data of the return series from Excel to Osmetrics. When copying it, it's better to copy it with the title, with the heading, so that the heading will just paste on Osmetrics, right? So if I do that, let me see. Okay. I just copy. I copy my return series. I'll paste it on Osmetrics. Just Control V, you can paste. So you see, if I paste it, the title is also there, the heading. So when copying the data, copy it with the heading as well and paste it. So now we have our data on Osmetrics. This is our data. It is here. You can see it. Okay, now the first thing we'll do is we'll check the properties of this data, because it is the properties of this data that will tell us what method to use. It will tell us if we can model it with traditional time series methods or if we can use the Garch-Type methods. Typically, before checking the properties of the data, I will tell you what to expect typically. So typically with high frequency financial data, we will expect it to be leptoketic. You know what it means, but I'll still tell you. We expect it not to be normally distributed. Of course, we are going to use the Jagbera test. We will also expect to have Ash effects. No, this ASH stands for autoregressive conditional heteroscedasticity. So if we have ASH effect, which is actually the volatility clustering, then we cannot model this data with traditional time series methods, like maybe ordinary least squares, for instance. We need to model it using the Garch-type models, which we are going to see. So typically, we expect leptoketosis, we expect not normally distributed, we expect ASH effect. Also, what we'll also check is if there is serial correlation in the volatility series. And again, we'll also check stationarity. Stationarity. Okay. Actually, let me tell you something. When we have, if we use prices, which of course we are not going to use, but with prices, most of the times it is not stationary. We'll see more about stationarity when we'll be doing time series methods. Maybe next week, I don't know. But generally, with prices, it will not be stationary, which means it does not have a constant mean, it does not have a constant variance. But when we take returns, when we convert these prices to return, it becomes stationary. But we need to confirm it. That's why we are going to include stationarity tests when checking the properties or the descriptives. And with stationarity, we have many different tests, like the ADF test and so on. I don't want to talk about that for now because we'll see it probably next week. But so this is what we should expect when checking the properties. We expect to have leptoketosis. We don't want it to be normally distributed. We expect to have ASH effect. We expect to have serial correlation in the volatility series. And because we are using returns, we expect it to be stationary. If we have these kind of things, if we find this kind of results, then we cannot model it using traditional methods. We have to use the Garch-type models. Okay, let's check together. So once we have data, come to this 3D, I use other models. But when we start modeling it, we'll use models of financial data, univariate Garch models and multivariate Garch models. For univariate, we'll do it if we have just one variable. For multivariate metrics. But now, because we want to check descriptives, so we are going to use under category, we'll use other models. And you see here under model class, I'll leave it. Now I'll click formulate. Why is it not coming? Just let me check. Now this is my return series. Click on it and shift it to the left hand side. Then just click OK. Don't change anything here. Now we are trying to check the descriptive statistics. Of course, you can include the basic statistics where we will have things like the mean, the variance, the standard deviation. We'll check the normality results. We'll do the ASH test to check if we have ASH effects. We'll do the box PS test on the raw series to check if we have serial correlation in the raw series. And this box PS on squared raw series will tell us if we have serial correlation in the volatility series. Then, of course, we have unit root tests. You see, if I click here, we have the ADF tests, we have the KPSS stationarity test, we have other tests, but let's use the ADF test. Okay, now if you see these lags, we can increase the lags. If you have a high number of observations, then you can use higher lags. For instance, if you have more than 2,000 observations, then you can use, for instance, like let's say up to 50 lags. So since we have, I think, 3,000 something observations, I can increase this lags to 50. Just click here, put a semicolon, and then add 50. So I increase it to 50. Here I also have 50. So the ones I've ticked, I'll tick normality. The ones that I have ticked, these are the ones we'll get the results for. If I click now, OK, now we have to select the test. This is because of the ADF test. Again, we'll see more about this probably next week when we'll be doing unit root tests and stationarity. I'll just mention some things now for you. With the ADF stationarity or unit root tests, we have 3 models. We have the model with intercept and trend. We have the model which has neither intercept nor trend, that is the non-model. And we have the model which has only intercept. So for instance, you see the model which has neither intercept nor trend, the model which has only intercept, and then the model which has both intercept and trend. The one which has both intercept and trend is the general model. It is the least restrictive model, so it's better for us to use it. So I'll use it. Then I will not change this. I'll leave it. I'll click OK. Once I click OK, I get the results. So now let's check the results together. Of course, you have the mean value, the mean, the average value, the maximum standard deviation. You can interpret it normally as to check the normality test. You know, skewness, ketosis, and Jagbera, they give us an idea of normality. So let's start with skewness. You see, check if it is statistically significant. You see that this value is less than 0. This is standard form, 2.13 times 10 raised to the power negative 56. If you punch in the calculator, you will discover that it is 0.00 and something. So it is less than 0, which means it is statistically significant, right? Let's use 5% as our alpha. So it is negatively skewed and statistically significant. Also, excess ketosis. You see, we have excess ketosis of up to 10, which means actually the ketosis value is 12. 13.5. But we're checking just the excess ketosis. You know, with a normal distribution, ketosis should be like 3. The value of ketosis should be 3. Anything above 3 is the excess, positive excess. Anything below 3 is also excess, but negative excess. So if it is above 3, it is positive excess ketosis, which means it is leptoketic. If it is below 3, it is negative excess ketosis, which means it is platyketic, right? So you see here, we have excess ketosis of 10, positive excess ketosis, which means it is highly leptoketic, and it is statistically significant because it is 0. Probability value is 0. So if you check, so you discover that it is leptoketic. That is what we want. So let's check the others. Let's now check the Jagbera test for normality. So this is the Jagbera test statistic, but we are interested in the probability value. You know the null and alternative hypothesis for Jagbera test, right? I'll write it. Null hypothesis tells us that normally distributed. Alternative hypothesis saying that not normally distributed. So those are the hypotheses for Jagbera tests. So if you see probability value is less than 5%, therefore we are able to reject the null. You reject the null and you accept the alternative hypothesis. So at 5% level of significance, it is not normally distributed, which is actually what we expect. So we can tick that. Next, let's check the Garch test. For the Garch test, I will write the hypothesis. So this is for the Garch test. Garch test. Now for the Garch test, what null hypothesis? The null hypothesis is telling us that there is no Garch effect. The alternative is telling us that there is Garch effect. You remember, as I told you some time ago, because with most of these hypotheses, the null hypothesis is telling you that there is no problem, while the alternative is telling you that there is a problem. So, of course, you know Garch effect is a problem because Garch is conditional heteroscedasticity, and heteroscedasticity is a problem. So these are our hypotheses for the Garch test. Now let's check the results. You discover that we have the results using 2 lakhs, using 5 lakhs, using 10 lakhs, using 50 lakhs. At times, the results might confirm each other, but at times you might have conflicting results. If you have conflicting results, then always go with the results using the higher lakh. If you have like high number of observations, if you have, let's say 2,000, 3,000, 4,000, or more than 2,000 observations, always trust the results of the higher lakhs. But if you have fewer observations, then you can use the results of the lower lakhs. So since we have like 3,000 something observations, if we have conflicting results, then we can trust the results of 50 lakhs. So, but let's check. You discover that for all of them, probability value is 0, 0, 0. You see all these probability values here as 0, 0, 0, 0, 0. So we don't have conflicting results anyway. So if probability value is 0, which means less than 5, what does it mean? It means we are going to reject the null and we are going to accept the alternative, which is telling us that there is Garch effect. Garch effect means there is autoregressive conditional heteroscedasticity, which actually means there is volatility clustering. So we have Garch effect. So I'll tick it. Okay. Next, let's check. You see here we have box Pierce cure statistics on raw data, and we have box Pierce cure statistics on squared data. Both of these box Pierce statistics are showing us if we have serial correlation or not. But then what's the difference? With the raw data, it is showing us whether or not we have serial correlation in the raw data, which in our case here is the return series. The returns we copied from Excel and pasted on Postmetrics. Do we have serial correlation on this raw data or not? That's what this one is telling us. But with this one, with the squared data, it is telling us if we have serial correlation in the volatility series. And this is the one we are interested in. So, okay, let's check this first one. By the way, you know the hypothesis for serial correlation, right? The null hypothesis is even written there. The null hypothesis is saying that there is no serial correlation, and the alternative is saying that there is serial correlation. So, null hypothesis is saying that no problem, no serial correlation, and the alternative hypothesis is saying that there is a problem, there is serial correlation. Those are our hypotheses. So, first, with the cure statistics on raw data, you see all the probability values are 0, 0, 0, 0. They are all less than 5%, which means whether we are using 5 lakhs or 10 lakhs or 20 lakhs or 50 lakhs, it doesn't matter. All probability values are 0, which means we can reject the null because our probability value is less than significance level 5%, and we accept this alternative which means there is serial correlation, but in the raw data, in the return series. Okay, even if we did not find serial correlation in the raw series, it doesn't change anything. Whether there is serial correlation in the raw series or there is no serial correlation in the raw series, it doesn't matter much for us. That's not our concern. What we are really interested in is whether or not there is serial correlation in the volatility series. So we have to focus on the squared data, not on the raw data. So again, you see all probability values are zeros at all the lags, so that there is no conflicting results. If we had conflicting results, let's say some of them were significant, some of them were insignificant, then we would trust the results of the higher lag because we have a high number of observations, as I mentioned before. So since all probability values are zeros, it means we are going to reject the null and accept the alternative, which means there is serial correlation in the volatility series. I'm insisting it has to be volatility series, not raw series, volatility series. So we found serial correlation in the volatility series, which is what we actually want. So those are the most important things. It should not be normally distributed. There should be Ash effect, autoregressive conditional heteroscedasticity, which is actually the volatility clustering, and there should be serial correlation in the volatility series. Okay, let me just talk about stationarity, then I'll come back. Next, if you go down, we can look at the stationarity test, the ADF test, that is the augmented decay Fuller. And again, we'll see more about this probably next week. So with the augmented decay Fuller test, what is the hypothesis? With the ADF test is actually a unit root test. The null hypothesis is telling us that there is unit root, while the alternative is telling us that there is no unit root. And if there is unit root, it means it is not stationary, non-stationary. If there is no unit root, it means it is stationary. We'll see more about that subsequently, but let me just explain. Now, to perform this test, we have the test statistics and we have our critical values. We have critical values at 1%, 5%, 10%, but then we are using 5%, so we'll focus on 5%. Actually, this ADF test is a one-sided test, one-tailed test. So in order for us to reject the null, the test statistic has to be more negative. It has to be negative. If this test statistic is positive, you cannot reject the null. So put it in your mind that the test statistic must be negative because the ADF test is a one-tailed test. I'll explain more when we are doing stationarity next week. But just know that it's a one-tailed test, so it must be negative. If it is positive, you can never reject the null. It must be negative. And if it is negative, it must be more negative than your critical value. If it is more negative than your critical value, then you can reject the null. But if it is less negative than critical value, then you cannot reject the null. So since our test statistic here is negative 33, which is more negative than this minus 3, it means we can reject this null. So we reject the null, it has a unit root, and we accept the alternative, which says it has no unit root, which means it is stationary. So of course it is stationary, and we expected it. Like I mentioned before, just by taking the return series, by converting the prices to returns, you make it stationary. But we perform this statistical test just to be sure. Okay, so we have gotten all the properties as we expected. Because of this, we cannot model it using traditional methods. In particular, because of the Ash effects and because we have serial correlation in volatility series, we cannot use traditional time series methods to model the volatility. We have to use the Garch models, or let's say the Garch-type models. We are going to use the Garch-type models to model the volatility. Okay. So that is it about the properties of our data. Now that we are sure, we have checked the properties and all the properties have told us that it is okay for us to use the Garch-type models, we can go ahead to use Garch-type models. You have to be very careful with this one in particular, Ash effect. If there is no Ash effect, then you cannot use Garch-type models. You know Garch, I told you that ASH stands for autoregressive conditional heteroscedasticity. So Garch stands for generalized ASH. The Garch model is actually the generalized ASH model. They just put the short form Garch. So we are going to use the generalized ASH model, and we also have other extensions to it, which I will show you, to model this volatility. But we have to be sure there is Ash effect. If there is no Ash effect, you cannot use Garch model. If there is Ash effect, and we also have these properties which we have checked, then we can use Garch type models, right? Okay. Now, how can we model it? Again, we'll come to this model 3D icon. Now we'll change these other models and we'll take models for financial data. Now, with models for financial data, we have univariate Garch models and multivariate Garch models. With univariate Garch models, we are trying to model it for just one variable, univariate, one variable. With multivariate, we have more than one variable, like two variables. Maybe we want to check the volatilities of maybe two different markets, you know. Okay. So in our case, we have just one variable, so we are going to do just univariate. You see, we have variable, just market index for the NASDAQ, one variable. Okay. This is my return series. I'll click on it. I will shift it to this left-hand side. Where I'll click OK. Now, you see here, AFIMA orders. We need to check the ARO-MA order. You don't just write whatever you want to write. You need to check it. So to check it, we'll use eViews to check it. Okay. How are we going to check it using eViews? First of all, I'll open eViews. I'll click here. I'll use unstructured, undated, so that I will just type in the number of observations. How many observations do we have? Let me see. I think 3,000 and something. Oh my God. How many observations we have? 3,162 is 64, but you know the first cells above the first two cells. Yes, 3,164. But you see the first two cells are not included. So we have 3,162 observations. Where is it? So I'll put here 3,162 observations. I'll click OK. I'll type data. Just type the name of the series. I'll press OK. I'll just copy now the return series from Excel and import to eViews, just as we normally do on eViews, right? my God, I messed up. Copy. So I'll paste it in the first cell here. I can now delete this. Once I've pasted it, before doing this, I forgot to mention, before doing this, if you see, here is addings. I hope it's still recording. I clicked something. Let me just check to be sure. It's still recording. Okay. So on eViews, we have the addings. You see these addings? If I click on these addings, you see here download addings. Come to download addings. Then you look for Arima selection. You see, I already installed it, but in your case, maybe you have not installed it. You look for Arima selection and install. You have to install it, so you can look for Arima selection. For instance, if I want to install this one, if I click on it, then I can click install. So you look for Arima selection and you have to install it. You have to download it. But in my case, I already have it installed, so I'm directly going to use it. Close. So once I have put my data on eViews, this is my return series. Open it, just click on it. Once it is open, you come now to add-ins. You have to open it first before coming to add-ins. Then I'll come now to automatic Arima selection. I have it here because I have already downloaded it. I have already installed it. If you have not installed it, you will not have it here. If I click on automatic Arima selection, I have this information, automatically selected information based on Akaike criterion. We have Schwartz criterion and Aquin, but let's use Akaike. So don't change anything. Just click OK and wait for it. So you see, it is telling us that we should use 2, lack of 2 for A arrow for the auto-regressive part, and lack of 2 for the MA, that is a moving average part. We have A arrow and MA. So you see we should use 2, 2. So we should use an order of 2, 2. If I click OK here, I can delete this. You can see how it's selected. You see this one is highlighted with red, which means 2. If you go up here, you see 2, and if you come here, you see 2, right? So we are going to use order of 2, 2. That's what eViews is telling us. So according to eViews, our lack order is 2, 2, 2. So if I come again here to model, so for A arrow, I'll use 2. For MA, I should use 2. So please always use eViews to check the A arrow MA order. Okay. Once I have the A arrow MA order as 2, 2, now for the Garch orders, let's leave it as 1, 1. Most of the studies in the literature are using 1, 1, and they are saying that it is the best Garch order to use. So leave it here 1, leave it here 1, don't change it. Let's come now to model. Now you see we have different Garch-type models we can use to model this volatility. Of course, the first one is the Garch, which is the generalized hash. And then subsequently, they brought other extensions of it to try to solve some problems, because you know there are some problems with the Garch model. So other extensions of this Garch model came about subsequently to try to solve it. For instance, this Egarch stands for exponential Garch, and it is accounting for leverage effects. So the Garch model, the generalized hash, does not account for leverage effects. But if we are using Egarch, we are going to account for leverage effects. Secondly, for instance, we have Fiegarch. Fiegarch is accounting for long memory. Now, if you combine this Fiegarch and this Egarch, it will give you Fiegarch. So Fiegarch is accounting for both leverage effects and long memory, right? Egarch is accounting for leverage effects. Fiegarch is accounting for long memory. You see, Fiegarch is like saying that Fiegarch plus Egarch. So Fiegarch is accounting for both leverage effects and long memory. So for this course, we are going to see just the generalized Garch, that's a Garch. We'll see the exponential Garch, which is a Egarch, and we'll see the Fiegarch, which actually stands for fractionally integrated Egarch. So we'll see just those three: Garch, Egarch, and Fiegarch. For the others, you will see it for those who do the volatility course FINA 663. You will see the others. So first, we'll start with the Garch. So I selected Garch. Now, if I go down, I will not change anything here apart from distribution. With the distribution, you see we have Gauss distribution, student T distribution, get distribution, and so we are going to use student distribution. It is the best distribution to use for the Garch model. So that is the only thing I will put there. Then I'll just click OK. I'm not changing anything here. I'll use the default. I'll click OK. Again, I will not change anything here, and I'll click OK. Then I'll wait for the results. We have the results. We don't have good results. Let me see. No convergence, no improvement in line. Our results are not good results, so we cannot use it. Let me check the others. Let's try Egarch. I'll come back to Garch. Still no convergence, so there's a problem with this data. We cannot use this data. Let me check if it's going to work with a different distribution. Let's try. Normally we're supposed to use a student T distribution, but let's try with the get distribution if it will work, if we can have good results. Still we don't have good results. So if that's the case, then I'm going to use a different data. This data has problem, so I'm going to use a different data. Okay guys, let me close this. Sorry. Are you sure? Yes, please. No. So there is a problem with that data. It's not giving us good results, which means we cannot use it. So I'm going to use this data has problem. I'll use a different data. Save, don't save. Why is my laptop not responding? Okay. Let me look for a different data we can use. FINA 663, there's one data we used with Migauja. I think we can use it. My laptop It's freezing. Oh my God. Okay, this is the data we used with when I took the volatility cost. Yes, current price divided by previous price. Okay, so I'll use this data. Let's use this data. I'll open Osmetrics. So I'll come to File, New. So again, don't change anything here. Just write the number of observations. So I'm going to check how many observations I have. So I have 4,041 observations. 4,041 observations. So I'll directly copy my data from Excel and paste on Osmetrics. I hope data with the title, please. So if I come now to model financial data, we can check the descriptives just as we have checked before, but we have already checked it for the other data. So I'll just go directly to model the volatility. But remember, with the descriptive, use the Garch-Type models, you should expect to have this kind of properties. Most importantly, it should be hash effect and serial correlation in volatility series using the squared data, not raw data. So you expect to have this kind of properties of financial data. So I'll just move check the so we have 4,041 observations. So if I click here, I'll use unstructured undated. I have 4,041. If I click OK, I'll type data and just type the name of the variable. Then I'll paste my data here. Is that copy? Copy. I'll paste. Why is not pasting? Oh my God, I don't know what's happening. I'll copy the data again. My laptop is really misbehaving. I don't know what's happening to it. It should be 4042, I think. 4042, not 4041. This is 4044. It should be 4042. This, let's say this. I don't know. I wrote 4041 before, so I'll just delete everything. Save no. $4,042 based, so I can paste it there. Okay, delete. Now this is the data. If I open it, come to addings, you see automatic ARIMA selection. Remember, you have to download it first, you have to install it. Just click OK, don't change anything, and just we wait for it to come. So we see the automatic ARO MA selection is 2 2, so we'll use 2 for ARO and 2 for MA. So in Osmetrics, here will be 2 2. Okay, it's fine. For Garch, we should use 1 1. For models, again, I will start with the generalized Garch, the Garch model. Then here I will use student distribution. It is the best distribution to use for the Garch model. Don't change anything here, click OK. Don't change anything, click OK. And wait for it to come. Okay, we have good results now. We can interpret. So now with the Garch model, we have two important constraints. The first constraint is that the positivity constraint. It should be observed. So you see it is written here that the positivity constraint is observed. You see our estimated alpha parameter is positive and it is significant. The beta is positive and it is significant. So the positivity constraint has to be observed. Also, alpha plus beta, the constraint has to be less than 1. So you see here it is 0.97 and it is less than 1, which is fine. So the positivity constraint should be observed. And here, this value here, 0.97, should be less than 1. At times, you can have this value which is greater than 1, which is a problem. It should be less than 1. So if those two constraints are satisfied, then we are fine. Okay, now, after estimating each of these models, if you check and the constraints are fine, if the constraints are not fine, then it's a problem. We cannot use the model. But if the constraint is fine, they are fine, then we want to use the model. First of all, we should make sure that this model has solved these problems. Remember, we found that our data had Garch effect, the return series had Garch effect, and the serial correlation in the volatility series. These two things are problems. So that's why we are trying to model the volatility, because we are trying to solve these problems. So after modeling it with the Garch, we need to check to see if it has solved the problem, if it has eliminated the Garch effect and the serial correlation in the volatility series. So what we can do is we can come to test. That is, we'll click this test icon. We'll tick this box for test, and then we'll click OK. Then we'll check again the results, the diagnostics. So you can tick the ones you want. For instance, we can use normality, we can use bulk pairs on standardized residuals. We can tick these ones. I don't think we need this sign bias test. Of course, we need hash tests. I think that's all we need. So since we have high frequency data, and here we have 50 lakhs, we can also include 50 lakhs here. We have a high number of observations, we can use 50 lakhs. So if you select those, what else we need? Just that. If I click OK, so again, we are seeing the results. You see, it is still negatively skewed, and it is significant. Jagbera test is less than 0, which is still not normally distributed, but that's not our problem. We are not interested in whether it has solved the normality problem or not. Most importantly, we are interested in if it has solved the hash effect problem and the serial correlation in volatility series. So, okay, now we'll check these cure statistics on standardized residuals and cure statistics on squared standardized residuals. Again, this one is just on standardized residuals. So it's telling us if it has solved the serial correlation problem in the return series, in the standardized residuals. But with the squared standardized residuals, which is actually what we are interested in, we are going to see if it has if it has eliminated the serial correlation in the volatility series. So for instance, like I told you, since you have high number of observations, focus on the higher lag. So here you see this probability value 0.01 is less than 5%, right? That's 1%. It's less than 5%, which means since it's less than 5%, what's the null hypothesis? The null hypothesis is that there is no serial correlation. So since this probability value is less than 5%, it means you reject this null and you accept the alternative, which says there is serial correlation. So we still have the serial correlation. It has not solved it. But that's not our interest. We are interested in whether it has solved serial correlation problem in volatility series. So we check the one for squared standardized residuals. So if you check for 50 lakhs, you discover that probability value is greater than 5. That's 0.5959. It's greater than 5%, which means you fail to reject because it is greater than. So you fail to reject the null. And what is the null? The null is telling us that there is no serial correlation in volatility series. So if you fail to reject the null, it means there is no serial correlation. So by modeling it with the Garch model, we have solved that problem of serial correlation, which is actually good for us. Now let's check the hash test. Since we have a high number of observations, we should trust the results for 50 lakhs. If you check probability value, you discover that it is greater than 5%. So we should check what is the hypothesis for hash test. The null hypothesis is telling us that there is no hash effect, and the alternative is telling us that there is hash effect. So because this probability value is greater than 5, it means we cannot reject the null. So we cannot reject the fact that there is no hash effect. So it means therefore there is no hash effect, right? So it has solved the problem of autoregressive conditional heterogeneity. So remember initially when we checked the properties, we discovered that there was hash effect and there was serial correlation in volatility series. That's why we had to model it using the Garch-Type model. And we have used the Garch model to model it, and we have checked again the properties, and we have discovered that there is no hash effect and there is no serial correlation in volatility series. So by using the Garch model, it has solved these problems. Since it has solved these problems, first, we check the constraints and we discover that the constraints were fine. Secondly, we have checked again and discovered that with the diagnostics, it has solved these problems. Therefore, we can use this Garch model. I will show you how to use it, right? Now, but then everything is fine with this Garch model and we can use it. But we cannot just use it because there are other models. We need to check other models as well. For instance, let me come here to models for financial data, formulate. Okay, let's try Egarch. So you discover that the Garch model is not the only model. There are different models. So even though everything is fine with the Garch, we cannot just say we'll use it directly. We should check other models as well. And if you check other models as well, you discover that you would find maybe 2 or 3 or more models where everything is fine with them. Everything is fine. So how can you now choose which of them is the best? At the end, you have to decide which one is the best using information criteria. I'll show you. So don't just say because everything is fine with the Garch model, I'm going to use a Garch model. No, you have to check the other models as well. And then all the models where everything is fine, you have to choose which of them is the best model using information criteria. So first of all, let's check the Egarch model. Remember, like I told you, the Garch model is the generalized Ash model, but because there are some problems with it, it does not take into account everything. They brought extensions of it. So for instance, we have the Egarch model, which is the exponential Garch. It is accounting for leverage effects, whereas the Garch model cannot account for leverage effects. So again, I'll leave 2 here, which the AMA selection, which we got from eViews. The Garch orders 1, 1. I will still use student distribution. So I'm not changing anything. The only thing I'm changing here is instead of Garch, I'm putting Egarch. I click OK. Don't change anything. Click OK. Don't change anything. Click OK. And then let's wait for the result. So we are interested in this theta 1, most importantly for us, theta 1. This is our interest. Now, with this theta 1, it has to be statistically significant. If it is statistically significant, it means we have leverage effect. If it is not statistically significant, it means there is no leverage effect. For it to be significant, this probability value has to be less than 5%, as you know. So if it is significant, then now we come and we check this coefficient. If this coefficient is negative, it means that bad news affects the volatility more than good news. But if this value here is positive, it means that it's the reverse. It means that good news affects volatility more than bad news. But then it must be statistically significant for there to be leverage effect. And if you see down here, we have no constraints, right? So since this theta 1 is significant, it means it is fine. The model is fine. We can also come to test and test again. We are trying to check the properties to see if it has solved the initial problems with the Ash effect and the serial correlation in the volatility series. So again, we have normality test, standardized, the same things we had before. If I click OK, let's see. So of course, you see it is negatively skewed and it is significant. You can check it, but we are interested in squared standardized residuals. You know, just standardized residuals is not telling us about the volatility series. So we are interested in the squared standardized residuals. Since we have high number of observations, we would directly check for 50 lakhs. You discover that here is probability value is greater than 5%, which means we cannot reject the null hypothesis. Therefore, there is no serial correlation in the volatility series. So it has solved that problem for us. Also here, with the Ash test for 50 lakhs, if you check probability value is greater than 5, which means we cannot reject the null. And what is the null? The null is telling us that there is no hash effect. You cannot reject it. So it has solved the problem. There is no hash effect. So we discover that everything is also fine with the Egarch model. With the Garch model, everything was fine with the constraints and with the diagnostics. Now with the Egarch, everything is fine. Okay. Model, still everything the same. Now let's check Fiegarch. So guys, this Egarch is telling us if we have leverage effects or not. This Fiegarch, this one Fiegarch, there are two of them, BBM and Jonkam, but Fiegarch is telling us if we have long memory or not. So this Fiegarch is like combining Fiegarch and Egarch, right? So it's checking simultaneously if we have leverage effect and also long memory. So if I take it, Fiegarch, again, student distribution, I click OK. And I don't change anything here, I click OK. I don't change anything here, I click OK. And I wait for the results. So it's estimating, let's just wait. Okay, we have the results. So this is our results for the Fiegarch. Now, since it is telling us if we have both leverage effect and long memory, it means, of course, we expect to have theta 1, because you know with the Egarch, theta 1 is telling us if we have leverage effect or not. And remember, it must be statistically significant, it should be less than 5. Now, it is this D Fiegarch. This D Fiegarch is what is telling us if we have long memory or not. Also, it should be statistically significant. Now, since it is negative, it means bad news affects volatility more than good news. Now, with the Fiegarch, D Fiegarch, since it is statistically significant, that is good for us. But then, in order for us to have leverage effect, this value must be between 0 and 0.5, right? You see, we have 0.47, which is between 0 and 0.5. Therefore, it means we have long memory. By the way, what is the meaning of long memory? Let me just mention that. Long memory in financial market. Long memory simply means past observations, they have like a persistent effect on future observations, right? That is, it is typical in financial markets. We're not typical, but in financial markets, it simply means the historical price movements, they have a persistent, like a lasting, like a long impact on the future price movements. So there is that link between the historical movements, price movements, and the future price movements. That's what long memory is. So for there to be long memory, this value should be between 0 and 0.5. And of course, it should be statistically significant, right? So here we have found the average effect and we have long memory. You see down here, no constraints. No constraints. Now we should check the diagnostics to see if the Egarch model has solved the problem for us. So come to this test icon, click on this test box, click OK, and you select what you have done. Click OK, and then let's see the results. Most importantly, we are interested in squared standardized residuals. So directly check for 50 lakhs because we have a high number of observations. if you see probability value is greater than 5%, therefore we cannot reject the null. So there is no correlation serial that solve the problem. And if you check hash test for 50 lakhs, also probability value is greater than 5. So you cannot reject the null. And you know the null is telling us that there is no hash effect. Therefore, it has solved the problem. So there is no hash effect. So you discover that with the 3 models we have used, we have used the Garch model, we have used the Egarch model, and we have used the Fiegarch model. For those 3 models, everything is fine, no problem. But then which model should we use? Which of them can we use? So you need to choose which of them is the best. And to choose which of them is the best, we are going to use information criteria. So come to this model, come to progress, don't click formulate again, come to progress, and you see these are the 3 models we estimated. Model 1, 2, 3. So select all 3 of them, and then click OK. So you see these are the 3 models. So we are going to select which of them is the best model based information criteria. We have 3. The one which gives us the minimum value is the selected one. For instance, if you see here is 3.62, here is 3.618, here is 3.612. So you discover that this is the lower value, right? So this one is selected. By the way, you see if you see there's an arrow, they put like an arrow here. So last model, which was the Fiegarch model. So the Fiegarch model is the best model according to this criterion. Also, according to this Hanan-Quinn, again, you see this arrow sign, it is down in the third model, which means the third model, Fiegarch, is the best. And also, according to Egarch, the Fiegarch is the best. So it's not like in all cases it will happen like this. In some cases, maybe Schwartz might select the first model, maybe Hanan-Quinn might select the second model, maybe Egarch might select the first. So you should go with the majority. The model which is selected the most number of times should be the model, should be the optimal model for you, the best model. So in this case, all 3 criteria are telling us that the third model. So we are going to use the Fiegarch model. That is the model we'll use. So again, what you should do is you can just estimate it again. Estimate the Fiegarch model since we have seen that it is the best model. So you see Fiegarch model, just estimate it again. So let's wait for the results. It's taking some time. You see, they say a starting estimation process. So it's still estimating. We have to wait for the results to come. Okay, we have the results. So since we have estimated the Fiegarch model again, now this is the optimal model for us. This is the best model according to the information criteria. So this is the model we are going to use. Now, what do I mean by using this model? Let's say we want to find we need volatility as a variable. Let's say we want to carry out a study, let's say the impact of stock market volatility on whatever. So we need stock market volatility as a variable, and we have modeled the volatility using different models, Egarch, Garch, Fiegarch, and then we have selected that the Fiegarch model is the best. everything is fine. It has solved the problem of hash effect. It has solved the problem of serial correlation in volatility series, and we have checked based on information criteria that it is the best model. Nothing is wrong with this model, so we have to use this model. So we need the volatility as a variable. Once we have this model estimated, come to test, come now to store. You see here store, click on this store, click OK. Come to conditional variance. This conditional variance is actually the volatility. So if I click on this conditional variance, and then I click OK, it will generate it for conditional variance. It has already generated it. Our initial variable we brought in from Excel, right? So you see now it has generated our conditional variance variable, which is actually the volatility. Copy it and paste on Excel or take it to eViews and use it. So if you want volatility as a variable to use, maybe you want to investigate the impact of volatility on something. So this is how we generate the. You can also check the graph. How can we check the graph? And second here you see graphics. You see here we have the return series initially we brought in, and then we have the conditional variance, which is actually the volatility we have generated. So click on it and then come to all plot types. You see here actual series. You can use actual series. So you see I can now delete this. So this is the graph. This is the graph of the volatility. So this graph is showing us volatility in that stock market. So you see here we have periods of very high volatility, and here we have like periods of low volatility. So you can copy this graph and paste and then try to explain. How can you copy this graph? For instance, you can come here to edit, come here, copy bitmap to clipboard, click on it, and then you can come maybe to your Microsoft Word or something, and you can just paste it, Control V. So you can copy it and paste it on Word in your thesis, in your paper, and you can interpret it. So you see here we have periods of high volatility, and we also have periods of low volatility. So you can try to find explanations for these kind of things. For instance, in that particular stock market, you can try to check in this particular years, on these dates, what was happening. Maybe something was happening, maybe there was a shock in the market, maybe the global financial crisis, maybe the COVID-19, maybe there was a war in the maybe Ukraine war, anything which caused this volatility in the stock market. So you can try to find explanations for these kind of things, right? So that is the graph. For the volatility, we can also draw the graph, not for the volatility, but also for the original return series. Let me show you. So I'll take this back to the right hand side. This was the original return series beast. I can take it to the left hand side and I can draw the graph. Click on all plots, actual series. If I click plot, so you see the one down, the one up is the conditional variance, the volatility which we have checked. The one down is the return series itself, which we got from Excel and brought to Econometrics. So if you notice with this return series, you see these are volatility clusterings. You see autoregressive conditional heteroscedasticity. You see high period, you see where you have high volatility is followed by high volatility, and then where you have low volatility is followed by low volatility. So we have this volatility clustering, and you see it is more or less stationary, like around the mean value, because we took the return, so it is more or less stationary. So that's how we can use the graphs. So basically, I think that is it for today. So just to summarize, what I've said is that when you download your data, you have the prices. You have to let the prices, and this is the full lean price. The return series we are going to use. We don't use the prices. We are going to use based on the return. Sorry, not prices. We'll use the return series, and we'll import it to Osmetrics, right? And then the first thing is the properties of the data. Most importantly, we have to have hash effect and serial correlation in volatility series. If we have these kind of things, then we cannot model it with traditional time series econometrics. We have to use Garch-type models, because with the traditional econometrics, classical linear regression model, you don't expect to have any heteroscedasticity, and you don't even expect to have serial correlation, and you expect it to be normally distributed, these kind of things. But with financial data, typically it is leptoketic, that is excess positive ketosis. It is not normally distributed. There is hash effect, which is the volatility clustering. There is serial correlation in volatility series, and because we take the returns, it makes it stationary. So typically we expect this kind of properties for financial data because it is high frequency. Now, when we check the properties and we see that we have this kind of properties, then we can use Garch-type models to model the volatility. Again, we have different Garch-type models. We have the generalized hash, which is the Garch. We have the Egarch, which is the exponential Garch. We have the Fiegarch, which is a fractionally integrated Egarch. And we have many others, as you saw in Osmetrics. So for this course, we are focusing just on these three: Garch, Egarch, and Fiegarch. But for the FINA 663 course, those who do it next semester, you will see the other models. So when you check those three models, you discover that Egarch is accounting for leverage effects, right? And you are checking theta 1. Theta 1 should be significant. If it is negative, it means bad news affects volatility more than good news. If it is positive, it means good news affects volatility more than bad news. Now, Fiegarch is checking both long memory and leverage effect. We have the theta 1 as well, and then with the long memory, we are checking the D Fiegarch. Also, it should be statistically significant, and the value should be between 0 and 0.5. If that happens, it means we have long memory. Now, you can check for the Garch, for the Egarch, for the Fiegarch. In some cases, maybe some of the models will not work. Maybe some of them you will have problems. Maybe the constraints are not satisfied. Maybe they have not solved these problems of hash and serial correlation, because after estimating each of them, you have to check the diagnostics again. Maybe it has not solved it. But you discover that in some cases, more than one of the models have worked. More than one of the models have solved these problems and everything is fine. So then how can we know which of the model to use? So you have to use information criteria to select which one is the best model. When you select that this one is the best model based on information criteria and everything is fine with the model, then you can use that model. You re-estimate the model, and then you can go to the test icon, and you can go to store, and you can download the conditional variance, which is actually the volatility series, and you can use this volatility variable in your study. Maybe you want to check the impact of volatility on whatever, it's up to you. And you can also draw the graph and try to find explanation for the graph. Maybe you see periods of high volatility, periods of low volatility. Try to find good explanations for these kind of things. So basically, I think that is that about that. Okay, so I will stop recording now and see you guys next week. So stop recording.